So our next speaker is Dr. Guanbo Wang. He is currently a postdoc at Harvard University, and he actually received his PhD in biostatistics from McGill University. He is currently working on a lot of research areas, and one of them is focusing on transportability in causal inferences that include the investigating heterogeneous treatment effects and also how to develop the method for survival outcomes and how to leverage external controls or indirect comparators. So, Guanbo, welcome. Floor is yours.
Today I'll be talking about the project, the first project of my postdoc, which is a small one, but like it's an interesting one. It's about transporting how to efficiently estimate the subgroup treatment effect using multi-source data. This is a joint work with my friend Alex Levis, who's a postdoc at the Carnegie Mellon, and also my postdoc mentor Isa de Habram. So talking about transportability, there are a lot of like similar words talking about like how to fuse the data together to obtain some desired target parameters. So it includes the transfer learning, the federated learning meta-analysis, and today we'll focus on transportability and generalizability. So we say like transportability in causal inference, mainly differentiated from others from the aspect of like we have a well-defined target population, and so we mainly focused on the causal questions rather than meta-analysis. It's like very broad and general, right? So within the transportability research, so there are a lot of potential motivations, including like pharmaceutical companies want to save some budgets, they want to borrow the historical controls, or like the FDA wants to reduce the bias and improve the precision. So there are various methods have been developed. It depends on the source, top population, the target population, their relationships, and of course the target parameters. Some methods estimate the ATE, some methods estimate the heterogeneous treatment effects, and also the specific aims, why we develop the methods, and the relative like the stakeholder. So today I'll be talking about like I'll be focusing on the following two data structures. So we assume, so for example, the left panel, in case one, we assume we have data sets from different sources. So as indicates the data source ranges from 1 to m. Right, so in each of the data sets, we have the information from outcome Y, non-continuous treatment A, and also the covariance X. So for now, we assume that each of the data source can contain or like possesses the same covariance X. For the case, when this is not the case, some previous work already have a solution, but it's not the focus of this work. So for now, we just assume that each of the data sets have the same columns of X. So our target population is the shaded area. It's just one specific data sources. So we call it the internal specific source-specific data source or target population. Right. So on the other hand, the second case, the red panel, we still assume that we have m different data sources. But our target population is shaded as green here, and we indicated this population as r equals 0, otherwise 1. So why this target population can be special with regard to other different data sources, because this interested data source can have some missing information of the outcome and the treatment assignment, right? So just like a very illustrative example that we have different states data from the American, like for the drug approval, but like we want to estimate the drugs in China, for example, but like the drug is not even available there. So this is one of the example that we want to estimate this the treatment effects within this external target population. By the way, I know that like it's like not very realistic. There are a lot of different things going on, but just for the illustration. So for these two scenarios, we have different target populations, right? And so for each source of the data, we do not constrain the source, the data from either clinical trials or observational studies or the pool of, or the combination of observational cohort and a trial. Right. So we also assume that there is an interested categorical effect modifier, which is denoted by X tilde. It's a categorical effect modifier, and our estimand in the first case, it would be phi AS X tilde, which is the like counterfactual outcome mean conditional on this particular target population, and also this particular effect modifier value, for example, the male or female, or like the middle age, right? And on the other hand, in the second case, we define the target parameter as similar. So psi AS X tilde is just like we conditional on this target population, which indicated by R equals 0. So now I want to talk about like why we are interested in this estimate. So there is kind of like a story. So in the beginning of the project, because I do stats, so we'd like to like define some fancy target parameters. So naturally, it would be like how to transport the heterogeneous treatment effect in general. For example, when the X tilde can be a continuous variable, or a high dimensional effect modifiers, or we just simply like let X tilde equals X, right? But like meanwhile, we also want to develop some mathematics, some statistical tools that the doctors or clinicians can really use in practice. So we talked to them, and so after the introduction of the project, I still remember the first sentence they said is like, "Oh, we know what we want to estimate or what we are interested in. I don't need others to tell us what we want to estimate." Well, like for the reason of confidentiality, I'd better not disclose any names, but it's in the end helpful for us. So for them, for some particular certain diseases, and so the clinicians, they are from like their years or decades experience and the position, they already know by heart that we know this variable is a strong effect modifier. And what will help us in the clinical practice will be, okay, so could you please tell us the effect or the effect estimate of this particular subgroup and their confidence interval for sure, and so that we can combine further with our like experience and the knowledge from the patients and the preference, etc., so that we can make a better clinical decision. So they seem to be like it seemed them to be like, okay, we have a known effect modifier, and it can be also like always like one variable, like female, male, or a risk score or an effect score. So for the reason above, so we say, okay, so we can have a small project just for estimating the subgroup treatment effect for their use. So this is like why we want to estimate this amount. Back to the project. For proceeding the estimation of a causal quantity, we need to make some causal assumptions. So the first three are the conventional assumptions made for causal inference. The first one, consistency. The second one, exchangeability. The third one, positivity. So just note that the third And the second, we just require those assumptions holds within each of the data sets, right? So we conditional as equals as. Assumptions 4 to 6 are the assumptions made for transportability. So the fourth one is kind of like the exchangeability, but not over treatment, but over the data source indicator. The fifth is the positivity, and the sixth is just like say that our interested population are well supported. And note that the assumption 2 and 4, the two exchangeability, one over treatment, the other over data source, combined together implies that the observed outcome is independent, like conditional independent of the data source, given a certain treatment. For this treatment, I personally, not personally, but like I don't think like the fourth assumption is quite nice in the way that it's not testable, and also it's just like a lot of people don't believe that. So later on, I'll mention a project that I'm doing for how to relax the fourth assumption. And then we also define some nuisance parameters. The mu A is the outcome model, and the QS is the source model, the probability of S equals S given X. And the eta A is just the propensity score, which is suggested to be estimated like by stratification. And kappa S is this common support, the inverse of the support. So under those assumptions, our estimators target parameter are identifiable. So by the way, like throughout this talk, I just focus on the case 1 and case 2 just follows. It's just like a trivial extension. So it can be either identified by the outcome regression or the weighting strategy. We want to, so sometimes like we have the data where X, the confounders or the queries themselves like are of high dimension, or when the relationships between the outcome and the queries are complex, it's hard for parametric models to capture the complex relationships. So that like we would like to use non-parametric or flexible machine learning methods to estimate the nuisance parameters, right? So non-parametric estimation of the target parameter can be facilitated with the aid of the non-parametric influence functions. So we show that the first order influence function is as such. It can be really like easy to parse. Is the first one is the outcome model, and the second one is just the de-biased term. But we further show that the semi-parametric efficient influence function stays the same when the propensity score in each source of data is known, which implies that when the data sets are coming from trials or part of the source are trials, then like the estimation and inference follows stays the same based on this influence function. So we propose to estimate the target parameter by just equating the empirical average of the non-parametric influence function to 0. So during the estimation, we propose also to use sample splitting and cross-fitting, just as Tong proposed. So this is our asymptotic theory. So if the nuisance parameter and their estimates and the second order of the second moment of the outcome are bounded, so of course those nuisance parameters, because they are a probability score or source model ranging from 0 to 1, so they are bounded from 0 to 1, we meant. And the nuisance parameter can converge at a relatively slow rate, like OP1. And then the target parameter, the difference between target parameter estimator and the true value can be decomposed into the following 3 terms. It's very similar to what just Tong said. So the first one is, it's a little bit different, but like the spirit is the same. So the first term is the empirical average of the influence function, which is 0. And the second term is the bias term, and the third term is the remainder, which converge at the root n rate. So let's take a closer look at the bias term Rn. So Rn can be decomposed or can be expressed as a very nice product term. So it's like suggests us that the estimator can be W robust in the sense that if either the outcome model mu A or the combination of the propensity score and the source model can be correctly specified, which means converge at the OP1 rate, then our estimator phi AX X tilde is also consistent, which again means converge at OP1 rates. But more importantly, if this the bias term can converge at the root n rate, then our estimator can be root n consistent, non-parametric efficient, and also asymptotically normal. So I'm very happy to hear that, like what Tong just said, so I don't need to explain again. So we just say like with sample splitting, we allow for estimating all the nuisance parameters using flexible machine learning methods such as GUM. And so GUM is OPN to the power of -2/5, which is like even like slower, faster than a quarter rate. So it just implies we can estimate all nuisance parameters using GUM. So recall that our estimates are subgroup treatment effects. So what if we have our effect modifier has like 5 or even more subgroups, and we are interested in those subgroup effects simultaneously. So that's relates to a problem like multiple testing, right? So we kind of like use the same data to do the statistical inference over and over again, so that the confidence interval derived from multiple testing of data can be misleading. In which cases we need to calculate or determine the simultaneous confidence bands, or like also known as the uniform confidence bands. So we propose the method for constructing the simultaneous confidence bands. So the first step is to construct I call it pseudo T statistics, which is calculated based on the bootstrap. So with mild conditions, then we can construct the simultaneous confidence bands by replacing the 1.96 as usual. For the confidence interval, we just replace that with the quantile of the pseudo T statistics. So this the rationale is similar to the simultaneous confidence bands construction proposed by Victor Chobotov and also Edward Kennedy, etc. So we just kind of like use this and adapt this technique in our scenario to construct our simultaneous confidence bands. So these are some simulation results. So the first is figure in our simulation, we assume there are 5 different subgroups, and we are simultaneously interested in those 5 different subgroup treatment effects simultaneously. People may ask like why it's like long here but short here, because like I made the different sample size. Just want to make the figure like beautiful. So the blue horizontal lines are the bias, and then these 2 lines one is for the standard deviation calculated from the influence function. The other is the Monte Carlo standard deviation. They are fairly close. And the red line is the coverage of the pointwise confidence interval, which under expectation is around 95%. And the blue line is over coverage, which is also under expected, because this is the coverage of the simultaneous confidence band. So this is to show the double robustness, and So we show that like only if both of the nuisance parameters are incorrectly specified, our estimators are not consistent. Otherwise, like this square is our estimator is consistent. So this is kind of like a contrived simulation to show that our proposed estimator is also rate robust. So the x-axis is the error rate of the nuisance parameter, which means like if, for example, if all the nuisance parameters are estimated within no slower than a quarter rate, the 0.25, then the y-axis is the rooted MSE adjusted by square root n. So we see that the black one is our estimator, is already plateaued after a quarter rate, where the plug-in estimator, the red line, is not. So it has to be like converge only after the n to the 1 minus 1/2 rate, right? So we show that our estimator is rate robust and is always has a smaller MSE than plug-in estimator. We further applied our methods to estimate the effects of polypyridine extended release on the effect of reduction of PNSS score for treating schizophrenia. So the more score it can reduce, the more efficacy it shows, right? So we have like 3 different trials from 3 different countries, and our subgroup can be like gender, baseline score, and age. So this figure shows the results where we stratify our subgroup, our population by gender, so female and male. So the results shows that like the trial 1 and 3 in like these 2 different countries, they show similar heterogeneity with regard to gender for this particular treatment. It says like the treatment benefits female more than male, whereas the second trial in the other country, right? So the other population, like the heterogeneity among the second trial is not is not that significant compared to the other. So which it's like kind of like significantly show that our methods like is useful, right? So we also have a software, our software called C-Metaphor. It stands for causally interpreted meta-analysis for R, and which allows us to use superlearners to estimate all nuisance parameters. So it can estimate the internal or external average or subgroup treatment effect, and this is one example. I don't have a lot of time, so I'll just be quick for some of my other projects. But this is general heterogeneity treatment effect estimation. It's not interested in that group of clinicians, but are interested of the other group of clinicians or doctors. So, but like it's more a statistical challenge. So we have basically 2 different methods. One like pseudo outcome regression, the other is projection-based methods. So we are kind of like comparing these 2 different methods in different scenarios and determine how to transport the general heterogeneity treatment effect. The other one is more interesting. So I talked about like how to relax the assumption for. So we, with the evidence from the empirical observation and also some previous comments and beliefs in epidemiology, people believe like the relative effect measure conditional on X is more transportable than the whole distribution of the counterfactual outcomes. So when we replace this assumption with this assumption, like starting from the identification, everything changed. So in a paper, we discuss the impact of this assumption in 3 different scenarios, and also developed a multipolarly robust and non-parametric efficient estimator. And we are doing like some survival outcome transportability and QTE transportability. Yeah, so this work, thanks to Gonzala, Miguel, and Jamie. Thank you very much.
Thank you, Guanbo, for this great talk, and also for introducing all of this very, very interesting topics and projects. Because we are slightly behind on schedule, so I'm going to ask, to reserve the questions for you toward to the end of the session.
Sure.
When we open the floor discussion, okay? Thank you so much.
Yeah, thank you.